So good afternoon or good morning, everyone, and thank you for joining us to this seminar. Today, we have the pleasure to welcome Corentin Caudron, who is Associate Professor at the Université Libre de Bruxelles. And he will discuss and present to us the use of continuous-based seismicity to monitor volcanoes. So, Corentin, the floor is yours.
Thank you. So there's a bunch of people which are listed here, but there's even more. So I'm not going to mention them all, but I will instead refer you to some references. You will see them below, at the bottom of the slide. So if you have any question, just ask it or interrupt me. There is no problem. I'm just going to start with a few slides. So you probably know that, but the main charge of volcanologists who are doing monitoring is to forecast the onset, the size, the duration, but also the hazards which you can get with eruptions. And we tend to do that by integrating observations. And there is an increasing trend now to also incorporate or use quantitative models to interpret our observations. So that's really something which is becoming crucial for people who are dealing with monitoring. So we still have quite many challenges. You can think about volcanology as a pretty young science in the sense that the first seismometers were only installed 150 years ago, more or less. So it's still a pretty young science. We're still learning, and we are facing what we call an observational bias. And this is quite easy to understand. It's a tricky word or complicated word, but it's actually quite easy. The fact is that we are observing volcanoes which are which exhibit very long life cycles with very short time series, because we've just started. So if you think of a volcano like Campi Flegrei in Italy, we have a big caldera system, we have lots of deformation, but the eruptions are quite rare. So we just have, let's say, 40 years at best of continuous data, and we have to extract information for a volcano which has very long cycles. The other thing which is quite important is that we have seen pretty recently big eruptions, so VEI, Volcano Explosivity Index of 5 to 6, but we haven't witnessed very much bigger eruption like VEI 7 or 8 with instruments at least. So we don't know what to expect before this kind of eruptions, which is a bit concerning, I would say, because we don't know what to expect. The other thing I would like to point out is that, as I mentioned, we've seen pretty small eruptions. So you see that you have here a figure of log damage fatalities on the y-axis and the chance of occurrence in any given year. When we deal with volcanoes, we have pretty mild or even pretty intense eruptions, but we haven't seen the big volcanic eruption VI 7 or 8. And we think that, well, at least the scientists who wrote this book chapter, it's actually a book, they think that if we were to witness that kind of eruptions right now, that would be a global catastrophe. So again, we don't have any information in terms of instrumental information about these big eruptions, VI 7, VI 8, but they will happen at some point. And they show you that, for example, St. Helens Vesuvius, VI 5 eruption, you have a chance of occurrence of that kind of eruption of 10%. So essentially, you can think about it of having the chance of that kind of eruptions every 10 years or so. Big eruptions that happen less frequently, but still that will dramatically impact the world and our planet. So what can we do? Well, we do something which we call monitoring, as you know, most likely. And there are many ways to monitor volcanoes right now, or nowadays you can install sensors at the surface, and that's what I'm going to cover today. For example, seismometers, you can install GPS, you can install tilt meter, multigas, for example, to just kind of extract information about the gas evolution. And then you can also observe volcanoes using remote sensing, of course, which is becoming super popular. That's very efficient. For example, in Iceland right now, there was the 6th eruption this year in Iceland a few days ago, And we have extremely interesting information extracted using INSAR, so using a satellite which provides us information about the deformation and dike intrusions, etc. So we can combine both or all these things together. But I'm going to focus today on the most basic instruments, let's say, installed on volcanoes, which we call seismometers, and which measure ground vibration at the surface. So something which is pretty important to think about or to have in mind when you get started with seismometers is that you have different types of seismometers. You can have the very, very fancy equipment, which we call broadband sensors, and which are very interesting because they provide us information down to 200 seconds of dominant period, which means that very slow movement, which can be related to magma movement, can be captured by these instruments, but they are expensive. So you need to probably spend something like $15,000 to purchase one broadband sensor. On the opposite side of the spectrum, you have short period instruments, sometimes even geophones, which have, as you can see here, good sensitivity between 1 hertz and 10 hertz, or 1 second, sorry, and 0.1 second. But you see that their sensitivity dramatically drops when it comes to very long period waves. And the good thing is that they are way more cheap, so you can purchase that kind of sensor with $1,000, for example. Then the other thing you need to be aware of when you do seismology on volcanoes is that you need to protect your instrument. So again, if you think about the very fancy equipment I described, the broadband sensor, let's say the Rolls-Royce of the seismometers, it's great, it's super sensitive, but it's sensitive to everything, which means that you can get vibrations which are induced by the wind, by temperature variation, and that's not exactly what you want on a volcano. You don't need an anemometer because you can purchase an anemometer. So we need to take some actions to protect our sensor. In that case, you can see that the seismic pier, the seismic platform, where the sensor is sitting, is decoupled from the walls, and that's a way to prevent any wind-induced vibration. But when you have all these things ready, and when your installation is pretty much complete, so I'm showing you here a few photos from an installation in Indonesia on the volcano of my PhD thesis, Kawajan, on Java Island. And you see that you need to dig, you need to install your sensor. But the cool thing that if you have many seismic stations, you can start, for example, to do imaging. So you can know a bit more about your plumbing system. So in that case, for example, the red dots show you earthquakes, and the earthquakes will, of course, trigger some waves which will travel from a source towards the seismic stations. And if you see that the waves are slowing down, or instead they are going faster, you can tell something about what's going on in your plumbing system. So if they slow down, it can be due to magmatic fluids or magma movement. And conversely, if they go faster, it can be due to just solid rocks like basalt. So that tells you something about the plumbing system. And yeah, something I forgot to mention, that if you want to compare a short period sensor, so let's say the cheap sensor and the broadband sensor, that's exactly the same seismic trace. It's an hour and a half here, seen by those different sensors. So on the above, on top, you have the short period sensors, and below you have the broadband sensors. And you can see that you have many more ground motions, and actually very low frequency ground motions, which you can capture with the broadband sensor. Okay, so you can monitor earthquakes. That's super useful, and that's the very first thing you will do at the observatory level. So what you are going to do is try first to classify the earthquakes. And unfortunately, on volcanoes, you have many different types of earthquakes. You can have what we call long period events. We have volcanotectonic earthquake, which are just traditional tectonic earthquake on the volcano. And then a joyful exotic signal like tornado. And that's, of course, super useful, very valuable, because that's the first thing you need to do when you monitor a volcano. Just going to show you an example from an eruption in Iceland in 2014, which was the largest eruption for 2 centuries in Europe. And when you have that kind of nice network, so you have all the triangles are seismic stations, so you see that the scale is pretty large. You can start to pick your earthquake, and in that case, it was super useful because in the end there were more than 20,000 earthquakes triggered during 2 weeks. That was due to a magma intrusion at depth, and the Icelandic colleague could track the evolution of these locations, and you can see that they were beneath an ice cap at 6 kilometers of depth, and then they migrated towards the north and finally escaped the glacier, which is a good sign in Iceland, because if the magma interacts with ice, it will fragment, and then you can get ash, and in that case, often you have to close the airspace. And you can see that in the end, after 2 weeks of magma propagation, the magma decided to erupt to the north outside of the glacier, and which was very fortunate for our Icelandic colleagues. And so that's what you would do first with your seismometers. As I mentioned in the title, I like earthquakes, don't get me wrong, but I also like noise, ambient noise, and tremor. And I'm going to cover a few things today. Most likely I will just stop after seismic interferometry and DSAR, and I will probably not cover the source, which we could discuss later, or I could give some information if needed later. So what is noise? Noise is anything but earthquake. So the noise is actually what you have most of the time on your seismograms, on your seismic velocity on the y-axis. So 95% of the time you will record some noise. And then sometimes you have an earthquake in blue here. And what is important to know or to understand is that this noise is triggered by interactions between the ocean. So the waves are triggering some, the ocean is triggering some waves which are coupling to the ground beneath the ocean, and then they will travel all the way through the crust, quite far away from the source, and you can actually detect this so-called secondary microseism, so these oceanic waves, all over the globe, 24 hours a day, 7 days a week. So these are mainly composed of surface waves, and that's pretty much true for any point of the globe where you have a decent seismic station. So that's what I'm showing here. You see that you have seismograms right here all over the globe, and what you see, these red colors are actually energy which is triggered in the ocean, in which you can, of course, get in Rwanda. You can get it in France, in Belgium, wherever, even in Tibet. And that's very useful because then you can do a bit of fancy processing. I'm not going to enter the details here today, but you do this pre-processing, and then you can extract some information about the crust. So by playing with the frequency, you can actually do some imaging, and that's one of the pioneer study which was published in 2005, because you don't need any explosive activity, any active source. You can just use those oceanic waves to probe what's going on beneath your stations. And that's, of course, very useful, very valuable. Without much surprise, this has been first studied by oil and gas industry, because you can image the reservoirs. Again, I'm going to cover something which is a bit different, the monitoring part of this seismic interferometry, and the principle is pretty easy to understand. You have waves coming from the ocean. Here we are at Piton-la-Fournaise in La Réunion Island. You have different seismic stations. I'm going to ask you to focus on PBRZ and NCR. And you can imagine that you have waves coming from the west. They will travel first at PBRZ, and then they will reach NCR. You see that you have direct waves. Those ones are in blue, but you have also scattered waves. We call them coda waves. They are in red, and those ones are refracted on different heterogeneities, and they will come much further away from zero on this so-called cross-correlation function. You don't need to understand what a cross-correlation function is, but essentially what you need to understand is that the positive part of the cross-correlation function are waves which have reached PBRZ station first, and then finally after a few seconds they will reach NCR. Of course, the direct waves will be less shifted with respect to zero than the red waves, than the Coda waves, because the red waves will take much more time to travel from PBRZ to NCR. And the opposite is right. On the negative part of the cross-correlation function, you have actually waves which have traveled first to NCR and then will reach PBRZ. And that's actually very useful, because that's, let's say, an image of your medium. If you do that every day, you get an image of your medium. And it's even more interesting when you start comparing your cross-correlation function, your image of the day, with a reference. So for example, if you have 1 year of data, you can stack, you can use all this data to construct a reference cross-correlation function. And you will compare, let's say, the cross-correlation function, the image of today, with this reference. And you can see that the red and the black curve on panel B are quite comparable, close to 0, but they are very different when you consider the lag time of -30. So the negative side, -30, you see that you have a big shift. And that's exactly what we are interested in, because this time delay, this difference of propagation in terms of time, is actually related directly to the seismic velocity change in the crust in your volcano. And that's the basic parameter I'm going to talk about within the next 10 slides, more or less. One of the first study which was published was in Science, and showed that you have here the seismic velocity change. You need to pay attention to the fact that Florent Branguet, who was the first author of this paper, at that time was flipping the axis. So negative is up and positive is down. But essentially what you see is that when there is no earthquake, there is nothing. And then you have a big earthquake, seismic velocity will decrease, then it will recover. Then you have a bigger earthquake, that's in Parkfield in California. You have a seismic velocity drop, and then again it will recover. So one way to think about it is that you open a big fault, you create a new fault in your system, and the seismic wave will slow down relatively, which makes sense because you open something new, and the seismic wave will take more time to travel from one station to the other. So that was the first big study, let's say, in the community. Then a few years later, that's one which is again related to an earthquake in Japan. In Japan, they have 1,000 sensors at the very least. So the island, the country is covered with seismic station. And you see that before Tohoku earthquake, the magnitude 9 earthquake in 2011, there's not much happening. Everything is pink. So the seismic velocity is close to 0%. I'm going to show you now the results of the seismic velocity change computation. And you see that you have red patches which have appeared just after the earthquake. So the very important thing here is to understand that this is not a precursor. This is right after the Tohoku earthquake. Still, it's very interesting because it shows that there are red patches, which means that the seismic velocity has significantly decreased, at least relatively. And this coincides with volcanoes. So at that time, Florent Branguet thought, and I think he's right, that it's a way to interpret where you have high volcanic fluid pressure. If your volcanoes become red, it means that they are more pressurized and they might be more prone to an eruption. So this again shows you that we can do some stuff with this noise, and just again need to understand that those waves, the excitation comes from the ocean. So they are there all the time, and you can do monitoring in a very cheap and efficient way. Getting back to the first study on volcanoes. So this is let's say the pioneer paper for the volcano community. It's again at Piton-la-Fournaise. You see on the upper panel the long-term variation. So this is pretty much 2 years of data, and you see that you can't see much. There's interesting variations. You have a long-term trend. What Florent did is that he subtracted the long-term trend from the black curve. And what he got is this panel B curve. So you see the dV/V again, the y-axis is flipped, which means that you see that before the eruptions, which are shown here as green rectangles, we have 1, 2, 3, 4, 5 eruptions, you see the seismic velocity tend to decrease. That's what he highlighted in red. And this is quite systematic. You see that when there's cyclones or pretty bad weather, it's difficult to reconstruct reliable information. What is even more interesting is that you see that the seismic velocity is dropping when there is no earthquakes. That's the panel C. So when there was no earthquake on Piton-la-Fournaise, the seismic velocity was starting to decrease. And then you see that there's an earthquake associated with the eruptions. So this shows, and this showed the community more than 10 years ago, that this could be a super interesting precursor to eruptions on that kind of system at the very least. And one way to understand that or to interpret that is that you open, again, cracks, tiny cracks, which do not produce any earthquake in the crust. If you open these cracks, the seismic velocity will take more, or the seismic waves will take more time to propagate through the volcano, and the seismic velocity will decrease, which was one of the first interpretations, which is actually still valid right now. So we started to, that's not me, but other authors, so Aurélien Mordet, who is now working in Denmark, basically applied the same methodology to Ruapeu volcano and found something similar, that the stations here, TUVZ, on the Ruapeu volcano in New Zealand, it seems to be exhibiting a seismic velocity decrease prior to an eruption, but a very localized decrease. So in that case, if you have many stations, you can start, and I'm going to show you a map later, to try to locate the source of your seismic velocity change. So the seismic velocity variations can be triggered or triggered by stress changes in the crust, but of course also by fluids. If fluids are ascending, rising towards the surface, that could change the seismic velocity propagation or damaging. So again, one way to sketch that or to represent that as a figure is that you have the normal state, then you open cracks in your system, and suddenly you will, or progressively, you will have a seismic velocity decrease. As I said, you can start playing with this, and in this case, we are in Indonesia on the right panel, and you see the situation at Merapi volcano in Indonesia, one of the most active volcanoes in Indonesia, and you see that it starts to be more complicated when you have a different seismic station. You see that this side of the volcano, the western side of the volcano, was actually showing an increase, whereas the center of the edifice was showing a decrease. So it's more complicated than what we thought in 2008. Then I had a chance to start playing with different volcanic data, and we started with a PhD student at Cambridge, at the University of Cambridge in the UK, to play with data from Kilauea, a very well-known volcano in the US, in Hawaii. And I was super excited. I arrived in Cambridge and said, wow, that's really impressive. We have a seismic velocity here on the left panel in blue, which matches almost perfectly the tilt. So tilt is a ground, is a way to extract information about the ground inflation or deflation. And you see that seismic velocity will increase when we have inflation, which is nice. I was super excited. We were already starting to think about where to publish that, etc. And then we compared that with Florent Branguier pioneer paper in 2008. And we say, well, it's great, but what Florent sees that when the volcano is inflating, the seismic velocity is decreasing. And we actually see the opposite, which is a bit concerning. So we started to think about how to interpret that. And we came up with numerical modeling to help us. So we use Coulomb stress software. And what we know about Kilauea, because it's a very well-known volcano, as I said, is that the source of the deformation is around 1 kilometer of depth. Whereas in the case of Piton-la-Fournaise, it's much deeper, so 3 kilometers of depth. And you see that if you compute the strain with Coulomb by just changing the depth of your point source, you see that the situation for Kilauea is that most of the volcano will experience compression, whereas in Piton-la-Fournaise, most of the volcano will experience extension. So if you compress the crust, you will close cracks. In that case, you expect seismic velocity increases, which is exactly what we see at Kilauea. And conversely, if you extend the crust, you will have a seismic velocity which relatively should decrease, which is what we observe at Piton-la-Fournaise. So that was one way, let's say, to reconcile some puzzling observations which we made at Piton-la-Fournaise and at Kilauea. So still dealing with magma, we process data from Iceland. So the eruption I mentioned earlier, Vadamunga Oluron eruption in Iceland. So you have the glacier right here, and you see the dike propagation, which is captured by earthquakes. You see nice seismic stations. So again, we have a great network here. And we were quite puzzled because when we processed the data again with Claire, we had some seismic velocity variation, which are changing yearly. So you increase, decrease depending on the season. You see the intrusion and eruption, which last for 6 months. Here, it's the gray rectangle in 2014, 2015. And then you see, for example, if you take, I'm just going to ask you to focus on station Fleur. Fleur is right here. The blue curve, you see that the seismic velocity has dramatically increased. If you take a station nearby, Thor, in red, right here, you see that the seismic velocity have decreased. Again, we have a problem here because we have stations which are just a few kilometers away from each other and which show opposite behavior. So what we decided to do is to call our friend numerical modeling, Coulomb software, and you see that you have red patches predicted by in terms of strain. Those places are actually experiencing extension, and in blue you have compression. And you see that Fleur is actually a place where we predicted compression, and indeed the seismic velocity has increased. Again, you close cracks, you will increase seismic velocity relatively. So that was an example of dike intrusion. Great, but we have more things on volcanoes, of course. What we have is that sometimes we have places where we have lots of water. I'm going to show you an example now of Wakari Wat Island volcano, which erupted recently. It's an island, and you have lots of water in what we call the hydrothermal, that is composing or building up a hydrothermal system. So again, we have lots of data here, so we could process continuous data for 15 years, more or less. We actually have more than that now. And you see the seismic velocity change here on panel B, and you see that we have lots of changes. This is an earthquake triggered a seismic velocity decrease. And then over time, you see that you have a long-term seismic velocity increase until what we call a gas-driven eruption, which is a phreatic eruption, which is an explosion, let's say, without any magma reaching the surface. And when we extend the time series until the last sequence of eruption, well, then not the very last one, because it was a more recent one a few weeks ago. But you see the seismic velocity kept increasing until the 2019 eruption. You have a sharp decrease, which shows you already that we have something much more complicated on these systems. But essentially what we think is that over time, if you have this kind of system full of water, you can decrease the permeability in your system. You can close cracks, mineralize secondary minerals in pores. And in that case, you would expect a seismic velocity increase. And that's what we've seen at quite many systems now. So since I'm running out of time, I'm going to skip this one. But we've seen the same thing, long-term seismic velocity increase before the deadly eruption in Japan in 2014, where 50 climbers were killed. And you see again the same pattern, seismic velocity increase over time and then sudden decrease. This is the red curve. And then you see that it becomes a bit more chaotic until the eruption. The very important thing to point out on that slide is that we only see that on top of the volcano, on the volcanic summit. We don't see this pattern elsewhere, which makes sense because hydrothermal systems are quite confined. They are not covering the full scale of your volcano, and we think that you can expect to see those changes only close to hydrothermal systems. I'm going to skip this. So the last thing I wanted to talk about is the fact that we see, unfortunately, on those volcanoes full of water, seasonal changes. And I told you that the groundbreaking study on volcanoes in 2008, there was actually an earlier study in 2006, which is a very interesting study and very important for the community as well. Again, Indonesian volcano, Merapi volcano, and you see here that during, let's say, a bit more than a year, you have a seismic velocity increase, then decrease, then increase, then decrease. What I'm going to ask you to take home is that those systems will just respond to seasonal variations. So if you put more water in the system, you will have a seismic velocity decrease. And when you have less water, when it's drier, the seismic velocity will increase. Unfortunately, not most volcanoes, but a lot of volcanoes are in tropical regions, and they are affected by this behavior, this seasonal behavior. And unfortunately, this will obscure your seismic velocity, which are related to the volcanic origin. And that's why we have to do some fancy post-processing right now. Okay, to conclude this part, DVV seismic velocity can change on magmatic eruptions, which is something we have seen on quite many volcanoes now. Often we'll have a DVV decrease, but that will depend on the depth. Sometimes you have a DVV which will increase if it's a shallow source, and conversely, it tends to decrease if the source of your deformation, of your stress change, is quite deep. When we deal with phreatic eruptions, with gas-driven eruption, no magma at the surface, we think that we have a DVV increase on the long term, which reflects sealing of the upper part of your system, and sometimes we have a decrease on the short term, which might reflect gas influx. Another very important point here is that this will largely vary spatially. For example, you've seen the dike intrusion, and it will depend on the season. So most often we need to do post-processing and numerical modeling. Okay, I'm going to finish this seminar with another technique we've developed over the years, which again, relies on continuous seismic data. Again, you need a station close to the summit. And you need continuous volcanic tremor, which is often found on volcanoes, which exhibit very large hydrothermal systems. So the fluid movement, the gas and the water will circulate, will convect, and they will create lots of vibrations, which you can capture at the surface if you have a good seismometer. Showing you an example of a volcano in New Zealand, when you see that all the time, if you take the spectrum, you have a ground excitation around 2 Hertz, which means that you have continuous tremor. So what we decided to do a few years ago is to, again, take continuous data from where we can. We have data which we have access through collaborations, and then some agencies like New Zealand, for example, they like to give you access to data freely, so you can download them from Belgium. And that's the example in the middle, Tongariro, and Ruapeu at the bottom plot. What we do is very simple, not going to cover the details here, but we compute the displacement every day. So seismometer will record the velocity, ground vibration in terms of velocity. We integrate to go to displacement, then we filter in 2 frequency bands, and we go above the tremor. We don't want tremor, because that would be a contamination. We are interested in medium change, not in the source change, not the tremor. So we filter between 4.5 and 8 Hertz and 8 and 16 Hertz, and we do a ratio between those 2 bands, low frequency divided by high frequency. And then we do some fancy, not so fancy, smoothing, rolling median, rolling mean. And what was very interesting for us when we computed that the first time is that prior to eruption at Kawajan in Indonesia, and you see that this so-called DSAR, that's how we decided to name it, seems to increase prior to phreatic eruptions. You see the situation at Tongariro again. Here it's a much longer time scale, so we have 10 years of data, and you see that over time it starts increasing until the eruption. Similarly, we have the same pattern at Ruapeu, again 15 years of data, and you see that it progressively increased until the first eruption and kept increasing until the second eruption. There was a lahar triggered here on the Ruapeu, and then it decreased. So we found at that time that would be a super valuable proxy to study that kind of eruptions at the very least, so those phreatic eruptions. Showing you the detail, when you are lucky, you have many stations, at the case of Ruapeu, and you see that the stations which are showing the clearest precursor are actually on top of the volcano. So it's DRZ, and not too far from the summit, FWVZ. If you go further away, it starts to be tricky to see a clear change. For example, the one in blue, NGZ, is 10 kilometers away from the volcano. Okay, that's great. That's a nice set of observations, but of course we need to interpret that to understand what we're seeing. So with Tarsilo Girona, who is currently working in Alaska, we designed a mechanistic model where we try to, let's say, divide the upper part of the volcano in 4 different parts. You have the magma, you have the gas pocket where you can generate some tremor, couple pressure to the conduit, and then you can generate some tremor, which will travel through a third region, which is the permeable cap. And then over time, for example, you can accumulate gas. That's what happens, we think, prior to some phreatic eruption, gas-driven eruption. And you see that the nice thing here is that the numerical model predicts that DSAR will increase in that case if you accumulate gas, if you increase the subsurface pore pressure, and in that case, you would increase seismic attenuation. So you would don't need to understand all the details, but essentially the model predicts that DSAR should increase, which was for us a good way to link our observations to a given process. And then we tested that on numerous volcanoes now, and so people have played in the lab to confirm our hypothesis, and they found some very nice results, which show that the pore pressure and the attenuations are increasing, that the DSAR in that case would increase. So some co-authors and collaborators started to try to look at shorter time. So I used a very long-term smoothing of a few months, and they found that we can actually find some very interesting pattern when we use this DSAR to predict very short-term changes prior to these eruptions, which we have published in 2022 in Nature Communication. You can see here that on multiple volcanoes, by using a template based on Wakari White Island eruption, so we use that template, which works very well, and then we use transfer learning, so machine learning, and use that template to see if we find the same thing on different volcanoes. And you see that we find this red blob here on numerous volcanoes, which for us is very interesting and promising. So now we are trying to leave this, let's say, the gas-driven eruption world and extend that to other type of eruptions, basaltic eruptions, etc. The interesting things also is that we found failed eruptions which were missed, possibly missed by the volcano when it rained because it was cloudy. And so we think that this could be a very valuable technology or methodology for volcano observatories. So to summarize, so we think that we should combine this noise-based, continuous-based seismic approaches on as many volcanoes as we can. So it's already implemented in real time at several volcanoes. And often we see long-term DSAR increase, sometimes with short-term decrease. I already covered the seismic velocity changes. But the last thing I wanted to mention is that all these codes, all these methodologies are available for the community. So there's a software which is called MS Noise, which is mainly developed by Thomas Lecoq at the Royal Observatory of Belgium. There are many contributors. It's installed at several volcano observatories. And you have the same sort of software for volcanic source or volcanic tremor of SAISNet. And yeah, feel free to reach out to us and to ask any question if you have specific question about the software. I'm going to leave it here for the seminar, and we'll take any question you guys have. Thank you.
Okay, thank you very much, Corentin, for telling us so much about this noise and how to use it for monitoring volcanoes. So the floor is now open for questions. So you can either unmute yourself and ask your question or put it in the chat. Any question? We have some comment in the chat telling us that it was very interesting.
Thank you. I will, of course, reply.
Okay, so any question?
Don't hesitate. Even naive questions are most welcome.
Okay, so maybe okay, we have one question. Let me go to the chat.
Okay.
Does the absorption of wave vary by rock types at different frequencies?
It's a very good question. It indeed varies depending on the rock type. So you can expect different things. For example, if you take very hard rock like basalt, andesite, you have a completely different seismic velocity compared to tephra or very altered material, which is super interesting for both imaging and monitoring purposes, because for imaging, you can then detect very well, do some tomography, for example. For monitoring, it means that we have to take that into account if, for example, the properties of the rocks are changing. And it's something we are exploring now with lab experiments with Mike Heap, for example, at the University of Strasbourg. And there is a person I mentioned in New Zealand who also did that recently. So that's totally relevant, and indeed it will vary depending on the rock types and the frequencies indeed.
Okay. Any other question? Okay, so I'll probably to take that further, does that mean we can get gas content?
Unfortunately, no. It's difficult to estimate like the absolute gas content. But what we think is that we see relative change of gas. So in general, what you would need to do is to get information from the multigas or from the SO2 flux, for example, or SO2 emissions using tropomy, and then you could probably try to estimate the gas content. But it's difficult to extract that information directly from the seismic velocity, the relative seismic velocity.
Okay. I have a silly question, like what do you do when you have volcanoes which are not well monitored, like not well equipped, there is not an observatory next to it? Pinatubo, for example, was like this, right? He was in the middle of nowhere and we had no idea. So
so definitely not a silly question. And it's actually one of the big questions we have, because what I showed you in the very beginning is that you need a pair of stations, and that's actually wrong. You need just one sensor. So what we are trying to do now with PhD student from Indonesia is to revisit this, so we can actually extract or estimate the seismic velocity change just with one station. And often it's much better than the pair of stations because there is less attenuation at high frequency. So you can probe the most shallow parts of the system. You can go to much higher frequencies. And that's actually very valuable when it comes to gas-driven eruptions, phreatic eruptions, because sometimes all the changes are quite confined close to the surface. The problem is that you need a station on top of your volcano, which is obviously risky and dangerous. And as you said, sometimes there is no station. So the first thing you will need to do is to install a station as close as you can to the top of your volcano, which is dangerous. But at the same time, you get very interesting information. So what we're trying to do now is to do that on, let's say, volcanoes where there is only one sensor, and see what we can extract with some very preliminary interesting information. So Ontake was one example where I only computed seismic velocity using single station approach.
Oh, okay. Thank you, Corentin. Okay, we have other question now.
Yeah.
So does the temperature of the magma matter?
Yes, it does. So you're right that would matter. It's a bit the same as the gas content. It will change. Well, it should change the seismic velocity you observe. And again, you could do imaging and monitoring, taking that into account.
Okay. But would it be possible to make some correlation? So we have a guess of the temperature or the temperature change?
Yeah. Again, I think we should approach that with numerical modeling to get some insight. But yeah, that's definitely something you could do.
Okay. So next question is, where do you source your sensors? Accelerometers are widely used in other industries, such as the aviation industry. Is this a possible source for cheaper equipment?
Yeah, so Charles is completely right, and that's actually what we do now. Instead, so I wouldn't say that broadband sensors are not valuable or let's say conventional seismometers. But yeah, you can do that with accelerometers. We also have purchased recently geophones, for example, which are cheaper and you can use them. And I've seen a question about distributed acoustic sensing by Harry. So that's the last question. And just to make the link, yeah, that's also what we are trying to test now. So there is already some study doing distributed acoustic sensing on volcanoes. The main problem we have with DAS, so I have two DAS, well, one DAS now and soon another one. It generates a huge amount of data. So we have to find strategies to first acquire continuous data, because you need to think about at least a few gigabytes of data per day for 1 kilometer of cable, for example, depending on the resolution frequency you choose. So there are very few volcanoes where we have continuous data. So we have, let's say, 1 month of data at best with distributed acoustic sensing of volcanoes, but I'm pretty sure that it's the future of volcano seismology, and I'm not the only one to think that way. So yeah, I think that's the next generation of studies for us.
Okay. Okay, actually, there was a follow-up with the temperature of the magma and its importance. Like, there was a comment, like, for example, the magma in Odonio Lenga is cooler compared to other magma because of its silica content. Does this affect the model?
It would surely affect, well, it could theoretically affect the measurements. The problem is that we are computing relative changes. So if you play with the same magma, well, let's say if your magma composition is not changing over time, you shouldn't, well, the change you will see will not be related to the change of composition. But this being said, it's quite funny because we'll start soon processing the data of Oldonio Lengai with seismic velocity or seismic interferometry. So that's something we plan to explore. I would just, in that case, approach this problem with imaging, so tomography, to see if the composition of this very different or exotic composition is showing us something interesting. But yeah, on the relative base, we should see a change.
Okay. Any more questions? Yeah, the last one was, is distributed acoustic sensing, you've responded to that one.
Yep.
Okay, so if there is no more question, I would like to thank again Corentin very much for his presentation. I think we never had a presentation really on this topic, so it was very good for this series. So thank you, Corentin. And thank you everyone for joining us this afternoon or morning.
Thank you for the invitation.
Thank you.
Bye-bye.